Welcome to
Yes,
Dr. Ahmed Zahir lecture series. Today, first of all, I welcome Principal Dr. Mazhar Ahmed Farooqi, IQC Coordinator, Professor Aditi Bhattacharya, my colleagues in the institution, and dear students. Welcome you all to the today's lecture on theory of relativity, which will be delivered by Dr. Sheikh Mohammad Wasim, Department of Physics, Maulana Azad College, Aurangabad. Now, to introduce him, I request Dr. Ifra Fatima to introduce him in short.
Good evening to all. I am Dr. Sheikh Ifra Fatima, Assistant Professor and Department of Physics, Maulana Azad College. It gives me immense pleasure to introduce my colleague, Mr. Sheikh Mohammad Wasim. He is presently working as a Assistant Professor in the Department of Physics and Electronics at in Maulana Azad College, Aurangabad. He is a young, enthusiastic, good academician, and a good teacher. He has completed his master's degree in physics from SRT-MU University, Nanded. He qualified GATE exam twice in 2020 and 2021. He also qualified SET examination in physics in the year 2020. With this brief introduction, I would like to invite Mr. Sheikh Wasim to deliver his talk on the topic theory of relativity.
Good evening to one and all. Thank you, Dr. Ifra ma'am, for introducing me to the viewers. First, I express my sincere gratitude to principal of our college and president of this lecture series, Dr. Mazhar Ahmed Farooqi sir. I extend my thanks to the vice principal, Dr. M.A. Bari sir. I express my thanks to the convener of this Dr. Ahmed Zahir lecture series, Professor Arif Pathan sir. I express my thanks to the coordinator of this Ahmed Zahir lecture series, Professor Dr. Sayyid Sultan sir. I am thankful to Dr. Aditi Bhattacharya ma'am, IQAC coordinator. So my today's topic of discussion is theory of relativity. Let me share my screen. So my today's topic is theory of relativity. The objectives of my today's topic is to understand the meaning of relativity, frame of references, universality of the physical laws, Galilean relativity. Then we will look at the Michelson interferometer experiment, and then we will look Einstein special theory of relativity, then time dilation, length contraction, and relativistic mass, and then we will have a overlook over Einstein's general theory of relativity. So first, to understand this all theories of relativity, what we should understand is what do you mean by relativity? So relativity is nothing but the fundamental study of how different observer views the same reality. So I will explain that relativity concept by considering an example. As you can see in this first picture, a person is standing in a train with holding a ball in his hand, and second person is standing on ground. Now an event occurs that the person standing in the train throws the ball. Now the person who is looking at that event from ground will measure some velocity of that ball, and the person who is standing inside that train, he also measure the velocity of that ball. And surprisingly, the velocity of the ball for the person who is standing in train will be smaller than the velocity measured by the person who is standing on the ground. This is very simple to understand. Why? Because the person who is looking at that ball from ground will measure two types of velocities. One, the velocity of ball itself, and second, the velocity of train. So the third picture is depicting how they perceive the velocities differently. The person standing in train will say that the ball is slow, and the person who is standing on ground will say that the ball is fast. So who of these two are correct? So according to laws of physics, both are correct in their own frame of references. Now, to understand this, we should first understand what do I mean by frame of reference. So frame of reference is nothing but the set of coordinates attached to a given rigid body. If we want to do measurement in physics, we consider some set of coordinates attached to the given body, and that set of coordinates is only what the frame of reference is. So you can consider this example. In this example, there are two observers. They are looking at some event. What can be that event? That event can be anything, like throwing of ball, flashing of light, the propagation of sound. That can be anything that is happening somewhere in the space. And both of the persons in frame first and frame second, they are observing at that event. Now, the person one will measure some different coordinate, and person second will measure some different coordinate. And I have attached a clock to both set of coordinates. So for first observer, the event will be measured as x1, y1, z1, and t1, and the second person will measure the same event s2, y2, z2, and t2. So this is how we can define the frame of reference. So in short, frame of reference is nothing but the set of coordinate attached to the given rigid body, and the measurement which you are going to do in that frame of reference will be different from other frame of reference. So basically, frame of references are divided into two types. One of the frame of reference is called as inertial frame of reference, and second one is called as the non-inertial frame of reference. What is inertial frame of reference? The inertial frame of reference is that frame of reference in which Newton's first law is valid. The word inertial is derived from the word inertia. According to Newton's first law, any object continues its motion, state of motion or state of rest, unless and until it is acted upon by external agent. So it means that those frame of reference which are at rest or which are traveling with constant velocity, they can be considered as the inertial frame of reference. For time being, you should just consider these two frame of reference as inertial frame of reference. So one frame of reference which is at rest is inertial. The second frame of reference which is moving with constant velocity is also inertial. Now what is non-inertial frame of reference? Non-inertial frame of reference is that frame of reference in which Newton's first law is not valid. What is Newton's first law? The first law I have just mentioned, that the body will not move unless and until it is acted upon by external force. So for time being, you should consider that those frame of references which are moving with non-constant velocity, or which are having the variable velocity, or in short, I can say the frame of references which are accelerating, they are non-inertial frame of references. So for my entire discussion, I will be restricting myself to the inertial frame of references. The inertial frame of references are those frame of references which are either at rest or moving with constant velocity. Now, my next concept which I'm going to discuss is Galilean transformation. If one person is measuring some event with some set of coordinates, and other person is measuring the same event with other set of coordinates, then there should be some mathematical formulation by means of which I should connect these two set of events. So for using the transformation, this is Galilean transformation, and then we will look at Lorentz transformation. So what is Galilean transformation? You can see that at time t equal to 0, the frame A and frame B both are coinciding with each other. So you cannot differentiate which frame is frame A and which frame is frame B. But as time passes, the frame B start to move with velocity v towards the right. So you can see in this animation that at initially both frames are coinciding, and at later point of time they are getting separated. So if I want to correlate the parameters measured in these two frame of references, I will use mathematics. So in this picture you can see that an observer is there who is standing in this S frame, and there is an observer. This is first observer and this is second observer. So this is second observer who is standing in S dash frame of references, and they both are looking at an. What can be that event? That event can be anything. For time being, I am considering that event is the motion of a particle. If the position of that particle, if I want to measure from this S frame of reference, as you can see from the S frame of reference, the position of this particle will be X. And similarly, the position of this same particle from other frame of reference will be X dash. So X is the position of that particle from first frame, as X dash is the position of the particle from second frame. And as I have told you, that second frame is moving with some constant velocity v in x direction. So we know a basic formula, that is velocity is equal to distance divided by time. And it can be rearranged to obtain the value of distance. So distance is equal to velocity into time. So after time t, this frame will be moved by distance vt. This v into t is having the dimension of length. So this vt is the distance between these two axes. If you look in this equation, this x dash is difference between this capital X, that is total X, minus this vt. So I have written that here, that is x dash is equal to x minus vt. And for y dash and z dash, there will be no change. Why? Because my frame is moving along the x-axis. So if my frame is moving along x-axis, I will not be worrying about y-axis and z-axis. So whatever measurement I'm going to do along y-axis and z-axis, that will be same. So that's what I have written here. And one more thing, the time in the both frames will flow at the same rate. So whatever time the person first is going to measure, the same time will be measured by the second person. So these are called as the Galilean transformation equation in S dash frame. Same set of equation I can write in S frame. They are called as the inverse Galilean transformation equation. So if I want to calculate the velocity of this particle, first what I have calculated? I have calculated the position, that is x dash, y dash, z dash and t dash. If I want to calculate the velocity of this particle, what I should do? As we know from the very basic laws of physics, that velocity is equal to the rate of change of displacement. So if I will differentiate this x dash with respect to time, I will obtain the velocity in that frame of reference. So that's what I have done here. So Vx dash can be obtained by taking time derivative of x prime, and this will be equal to dx minus vt upon dt, and finally I am getting Vx minus v. Similarly, if I want to calculate velocity along y direction, I will take the time derivative of y dash. If I want to calculate velocity along z direction, I will take the time derivative with respect to time derivative of z prime. So in this way, I can summarize this velocity transformation equation as this. So these are the velocity transformation equation. These are the equation by using which you can correlate the velocity in S frame and S dash frame. In same way, I can calculate the acceleration transformation equation. You should remember what I have done first. First, I have done the position transformation equation. Then by taking time derivative, I have derived the velocity transformation equation. And we know that acceleration is the time derivative of the velocity. So if I will take the derivative of this equation will be transformed into the acceleration transformation equation. So again, I have drawn the same diagram, and now I am taking the time derivative with respect to time derivative of the velocity to obtain the acceleration. And if I do that differentiation, what I observe is that this dv by dt, this term dv by dt, what this term is representing? This term is representing the rate of change of velocity with respect to t. But which velocity? Not the velocity of this particle. The velocity of this particle is vx dash or vx. But this v was the velocity with which your second frame was moving ahead with respect to first frame. And I have told you that both frame of references are inertial frame of references. It means this velocity is constant. If the velocity is constant, its differentiation should be equal to 0. That's why this term is getting neglected from this entire equation. And finally, I'm getting ax prime is equal to ax, ay prime is equal to ay, az prime is equal to az. So I can summarize this Galilean acceleration transformation equation as this: ax prime is equal to ax, ay prime is equal to ay, az prime is equal to az. Now I know the definition of force. If I want to measure the force acting on that particle in this S frame, this was my S frame and this was my S dash frame. This is my particle, and if I want to measure the force acting on this particle, if I want to calculate the force, we know the force is equal to mass into acceleration. So the observer which is there in first frame of reference, for him the force acting on this particle will be the acceleration in this S frame multiplied by the mass in this first frame. So it will be max. Similarly, the force measured by this second observer in the second frame of reference will be the mass into acceleration in this frame of reference. So in this frame of reference, acceleration of the particle is ax prime. So for him, the force will be fx prime, which is equal to max prime. So this is the force measured by first observer, and this is the force measured by the second observer. Now, from the Galilean acceleration transformation equation, I know that ax prime is equal to ax. It means that whatever acceleration this observer is going to observe, the same acceleration will be observed by the second observer. That's why if I use this equation ax prime is equal to ax, I can multiply this ax prime equal to x on both sides with mass, and finally this mass into acceleration is the force in x s dash frame, and mass into ax is equal to force in s frame. So from this, what I have got, that whatever force this person is measuring in first S frame of reference, the same force is being measured by the person who is standing in S prime of reference. So from this, I can say that the force measured by the two observers in two inertial frame of references is same. And you know, the all mechanical events in this universe can be governed by the Newton's laws of motion. I am specifically talking about the mechanical events. What are the mechanical events? Mechanical events can be a person who is throwing a ball, the two person standing on a platform, or throwing of ball, hitting of hammer. Any kind of mechanical event is governed by the Newton's laws of motion. And what I am getting from Galilean transformation equation, that force which is being observed from the both frame of references is same. So I can conclude that Newton's laws of motion are same in all frame of references, or the Newton's laws of motion are invariant under Galilean transformation. If Newton's laws of motion are invariant, it means they are retaining their form and expression in all inertial frame of references. From this, we can say that physical laws in universe are universal in nature. The word universal signifies that whatever event which is being observed by a person standing in S frame, the same event will be observed by the second person who is standing in S dash frame, which is moving with constant velocity. So this is suggesting us that there should be no absolute frame of reference. What do I mean by absolute frame of reference? It means that there is no preferred frame of reference, or the all inertial frame of references are equivalent in nature. But the way in which we have proved the Newton's laws of motion, can this thing be proved for the other phenomena of physics? Are the Newton's laws sufficient enough to define each and every phenomenon in the physics? Of course, no. There are certain other domains of physics whose laws can't be expressed or can be explained on the basis of Newton's law. Like if you want to study the nature of charge, the force acting between two charges, if you want to study the electromagnetic wave, if you want to study the magnetic field due to electric current, these are all the phenomena of physics which comes under the electromagnetic domains of physics. And for these laws, the Newton's laws are not applicable. To understand these phenomena, Newton's laws are not applicable. So which are the laws by using which we can understand these laws? They are the Gauss's law of electrostatic. This is giving the relation between electric flux and the charge. If you want to study the magnetic behavior, you uses the Gauss law for magnetostatic. If you want to study the relation between changing magnetic field and induced EMF, then we use the Faraday's law. Similarly, if you want to study the relation between the current and the magnetic field, then we use the Ampere's circuital laws. So these four laws which I'm showing you right now, these are the basic fundamental laws in electromagnetism. So these are the laws which depicts the electromagnetic behavior. Now, are these laws invariant under the Galilean transformation? Because we have already proved that Newton's laws are invariant under Galilean transformation. But what about these laws? So these laws were put into another mathematical construct by using the differential operators. This differential operator del, you can see the symbol here del. This del is actually given by I cap dou by upon dou x plus j cap dou by upon dou y plus k cap dou by upon dou z. So by using this del operator, what Maxwell has done, the Maxwell has converted these all laws which were in integral form into the differential form. So these are known as the four fundamental equation of Maxwell. This equation define and describe each and every electromagnetic phenomenon. Now, if we solve this the third and fourth Maxwell equation, and if I use some mathematics, that is vector algebra, and if I take del cross E, and if I solve this equation, finally I'm not going into discussion about this mathematical part. I will just tell you the final equation. So this is your final equation which we have obtained from Maxwell third and fourth equation. So this is one of the equation and this is second equation. This equation seems to be similar to the equation of a wave. So what does that mean? It means that these equations are representing some kind of wave, and these are the waves which we are calling as the electromagnetic waves. So these del square E is equal to 1 by c square dou square E by dou t square, and this second equation. These equations are representing the electromagnetic disturbances traveling through the space. There is one particular term which is coming in this equation, that is c square. What is this c? C is equal to 3 into 10 to the power 8 meter per second. So the electromagnetic disturbances are traveling with this much velocity in vacuum. Now, if I want to check the invariance of these laws under Galilean transformation, first I have checked the invariance of Newton's law. So Newton's laws were invariant under Galilean transformation. They were retaining their original form. What about this equation? If I want to check this equation, let's consider again an event is taking place. Is at this in this event, an electromagnetic wave is propagating like this, and the observer in S frame is observing that electromagnetic wave, and the observer in S dash frame is observing that electromagnetic wave. The electric field which the first observer is measuring is E, magnetic field is B, and position is X, and time is T. And the measurement of electric field and magnetic field by second observer is E prime, B prime, X prime, T prime. Now what I'm going to do, I am considering the Maxwell equation. This was the Maxwell equation. This Maxwell equation, this is the Maxwell equation in 3 dimensions. For 1 dimension, the equation will be like this. This is the equation in 1 dimension, that is along x-axis. So this is dou b by dou x is equal to minus 1 by c square dou e by dou t. So this is the equation which we have obtained from the Maxwell equation. Now I am going to check whether this equation is retaining its original form under Galilean transformation. So if I do the calculation, I have skipped the derivation. If I check this equation in second, the equation in first frame of reference is this, that is dou b by dou x equal to minus 1 by c square into dou e by dou t. So according to invariance of laws, I should have got the equation in second frame of reference as dou b prime by dou x prime is equal to minus 1 by c square dou e prime upon dou t prime. Why? Because according to universality of the physical laws, I should get the same equation as I'm getting in S frame. So in S prime, I should get the same equation as in S prime. But if I do the calculation, it is surprising to know that I'm getting this extra term. This is the extra term which I'm getting in the Maxwell equation. So where this term is coming from? I should have got this much term only, because universality of the physical laws tells me that it will be same across all inertial frame of reference. But I am getting this extra term. So this implies that Maxwell equations are not invariant under Galilean transformation. And this is a very big and a huge problem in physics, because two observers which are observing the two observers which are observing the same electromagnetic event, they are not agreeing upon the basic laws of physics. For the observer in S frame, he is telling something else, and the observer which is there in second frame, which is moving with some constant velocity, the both observer are telling the different result. It means that Galilean transformation is not valid for Maxwell equation. It means if the two observing in two inertial frame of references observe the same electromagnetic event, then they have to use different Maxwell equation. And this is against the law of universality of the physical laws. So it again ultimately means that if there are infinite number of inertial frame of references, then we need infinite number of Maxwell equation. This is not commonsensical, because I should have the same form or same law in all inertial frame of references. So this lead physicists to the experiment. So what could be the possible reason for this? So what physicists have suggested that this is because the Maxwell equation is true in one absolute frame of reference. And in that frame of reference, the velocity of light is c. If you remember the equation, this was the equation. C is the velocity of light, but with respect to which medium we are considering this velocity. If you consider the sound wave, you always say that sound wave travel with 340 meter per second with respect to air medium. If I consider the waves or ripples which are being generated on pond, then I say that waves are traveling with certain velocity with respect to that pond itself. But what about this C? This Maxwell equation is telling us that the electromagnetic waves are traveling with respect with velocity c. But this c is with respect to which medium? We must mention the medium with respect to which this c velocity is mentioned. So what physicists have suggested that there is an absolute frame of reference, and within that absolute frame of reference, the light is traveling with velocity c. And in that absolute frame of reference, Maxwell equation are true. And that's why we are getting this absurd result. That's why we are getting this extra term. So as physicists have suggested that there is existence of an absolute frame, we should be able to prove that existence. So this lead physicists to the experiment which can prove the existence of that absolute medium. And they named that absolute frame as ether, luminiferous ether. This is not the ether of chemistry. This is the luminiferous ether, which was the name given by physicists to that absolute frame of reference in which the Maxwell laws are true. And in all other frame of references, Maxwell laws should be modified. So different attempts were made by scientists to prove the existence of this ether. So one of the most famous and revolutionary experiment was done by Michelson and Morley. That experiment we are going to see. So this Michelson and Morley experiment is consisting of this apparatus in which you are having two mirrors. This is mirror 2 and this is mirror 1. A light, which is a monochromatic light, it is being thrown at a partially reflecting glass. This partial reflecting glass will reflect some of the light and it will transmit some of the light. So just have a look at this apparatus. The light is going like this. It is getting reflected, and then from mirror 2 it is again reflected back. So this is the ray of light which is going like this, and second ray of light is passing through this glass, because this glass is partially reflecting and partially transmitting. So this ray of light will be transmitted like this, and then from mirror 1 it will reflect back. Now the both rays which are reflecting back, this first ray and this second ray, they both will travel along the same direction. And we know in physics, if the two rays are traveling in one direction, they can show the interference phenomenon. What is the interference phenomenon? The constructive overlapping of the two waves or the destructive overlapping of the two rays. So if they are showing the interference phenomenon, we should observe the interference pattern, and that's what we are getting. So this was the basic apparatus which Michelson and Morley has used, in which they have used these two mirrors, and they have obtained friendship. But this is the Michelson interferometer at rest. And what they are trying to prove, Michelson and Morley is trying to prove the existence of that hypothetical ether, existence of that hypothetical medium which is existing in the entire universe. And with respect to this hypothetical medium, the light is traveling with velocity c. If light is traveling with respect to that ether, as we know that Earth is having an orbital motion around the sun. So this earth is also moving through the ether. So what they have tried to show, that if the earth is moving with respect to that ether medium, here I have written the direction of ether wind. So if earth is moving with respect to that ether, there should be some fringe shift, because the mirror, the light, when it is reflecting back from the first mirror, the mirror will move by certain distance, because earth is moving like this. And because of this fringe shift which we are obtaining, it should be the fringe which we are obtaining, it should be shifted by certain amount. And they have theoretically calculated that. If you look at it, if you look at this animation, then you can easily understand what Michelson and Morley did. In this way, the light ray is going and it is passing through the partially reflecting mirrors, and then it is coming back from the two mirrors. And this is the place from where we are observing that interference pattern. And now, since this Michelson-Morley experiment is done on Earth, the Earth is moving with certain velocity v, and this is how this Michelson interferometer is moving. And now they were expecting, they have performed the extensive calculation. This is the calculation which they have done. Basically, in this calculation, what we have done, the light ray which is traveling like this is one of the ray which is traveling in this direction. So if Earth is moving in this direction, the velocity of this ray should be the velocity of Earth, that is velocity of light minus velocity of Earth. This will be the velocity of light when it is going in this direction. If the light is coming back like this, after reflection, it will come back like this. Now Earth is moving in the same direction. It means that the relative velocity of the light should be c plus v. So one ray of the beam which is going towards c will have this much velocity relative to the ether. Ether is what? That hypothetical medium. And the ray of light which is coming back should have this much relative velocity with respect to ether. You can understand this example very simple, in a very simple way. If you are going on a bike and the other person is coming from the other side, then if you are going with 5 meters per second and other person is coming from 5 meters per second, then the second person appears to move with 10 meters per second velocity to you. That is 5 meters per second plus 5 meters per second. So in this way, if the two observers are moving in this opposite direction, their velocity get added. If it is v1, it is v2, it will be v1 plus v2. So this much velocity you will observe. And the other, by considering other example, if the person is moving like, if you are moving on bike like this is, if you are moving in this direction and other person B is also moving in the same direction, if you are having 10 meter per second velocity and the second person is having 15 meter per second velocity, so the velocity of the second object which appears to you will be 5 meter per second. Why? It will be 15 meter per second minus 10 meter per second. So same thing we are considering in this particular experiment. The one ray of light is traveling towards c with velocity c along with the velocity of Earth v. So the relative velocity will be c minus v, and the beam of light, when it is coming back, and Earth is going in the right direction and the beam is coming back in the left direction. So the relative velocity will be added like this and it will be c plus v. So the time taken by the beam to go in this direction and to come back to this point A will be different. And that time we have calculated, and which is equal to 12 upon c under in bracket 1 minus v square upon c square. Similarly, this particular platform has moved by a certain distance when the light beam is going upward and then coming back. So it will be like this. This will be the motion of light beam. Again, we have calculated this amount of time, and that amount of time is t2. And if I subtract this t2, I will get the time difference between the travel of the beam. What Michelson and Morley did, they have rotated this entire setup through 90 degree. If they are rotating it through 90 degree, the arm which was initially having length L2, now it will be having length L1, and this L2 length will now be of this particular arm. So they have moved that apparatus by 90 degree, and they have again observed the interference pattern. If we are moving the apparatus 90 degree, the time difference which we should observe is this much. So finally, let me explain this particular term. This is the time difference which they have calculated. And from this time difference, they have calculated the fringe shift. What is fringe shift? Fringe shift means there is a certain interference pattern, and if this apparatus is moved through 90 degree, it means that there should be some shift in the velocity, there should be some shift in the fringes, and that fringe shift which is calculated was having the value 0.37. So this was the theoretical calculation which they have done. So if we move the Michelson interferometer by 90 degree, we should observe this much fringe shift. तो आपका जो इंटरफेरेंस पैटर्न है वो 0.37 फ्रिंज से शिफ्ट हो जाना चाहिए. अब माइकलसन एंड मोरले ने जो माइकलसन इंटरफेरोमीटर डिजाइन किया था, that Michelson interferometer was so precisely made that it could measure even 1/100th of a shift in fringe. That is, it can even measure 0.01 fringe shift. This was the accuracy, 0.01. This much fringe shift can be measured by using Michelson interferometer. But when they have performed that experiment, they were expecting this much shift, that is 0.37 shift. But they have observed the null result. That is, if the interferometer is rotated through 90 degree, there was zero fringe shift. What does that mean? It means that the velocity of the earth with respect to ether is zero. That is, velocity of earth with respect to ether should be equal to zero. Then only this particular result is possible. But we know that earth is moving with 30 km per second speed around the sun. Then why we are getting the zero relative velocity between ether and earth? This can be only possible if there is no such medium like ether is existing. Because if we are having zero velocity with respect to ether, velocity of earth with respect to ether is zero, it means that there is no such medium like ether is existing. Then if no medium like ether is existing, then what about Maxwell laws? What are Maxwell laws telling us? The Maxwell laws giving us the behavior of electromagnetic waves. So if in that electromagnetic waves, in the equation of that electromagnetic wave, we were having a term of velocity, that is velocity of light c. And according to this Michelson and Morley experiment, the ether medium is not existing. But Maxwell laws and the Maxwell equation were derived by considering that there is certain medium like ether, and that in that medium the electromagnetic waves are traveling. So from this, what we have concluded that there is no such medium ether is existing. So different physicists came up with the different explanation to this ether, and this was the experimental setup of Michelson and Morley. This was the setup on which they have performed the interferometer experiment, and finally they have got the null shift. What Michelson and Morley thought that there is certain inaccuracy in their experiment. There is some uncertainty in their experiment, but this experiment were performed by different scientists at different locations in the entire world. And what result they have obtained, I have placed here. So this was the experiment which was performed by Michelson and Morley in 1887. So they also got the null result. And the last experiment was done by Jews in 1930, and they also got the null result. And this instrument which Jews has designed, that instrument was having more precision than Michelson and Morley interferometer. Their precision, the precision of the Michelson and Morley instrument was 0.01. This is the precision of the Michelson and Morley experiment. What Jews has performed, for that instrument the precision is higher, but still he is getting the null result. What does that mean? It means that there is no such medium is existing. It means that to explain this, no one was able to explain this behavior. Why ether is not existing? No one was having any explanation. Then Einstein came up with his revolutionary special theory of relativity. So according to Einstein has put forward two postulates. The first postulate of Einstein's special theory of relativity, that the laws of physics are invariant in all frame of reference. This was one of the postulates of Einstein's special theory of relativity. And second postulate given by Einstein was that the speed of light in vacuum is constant, independent of the inertial system, source and observer. No matter how you are traveling, no matter in which frame you are present, no matter with what speed you are moving, the velocity of light is always constant. That is, the velocity of light is invariant, or I can say that velocity of light is absolute. So if you consider this example, I am trying to explain you what is meaning of the absoluteness of the velocity of light. If you consider a person is throwing a ball who is standing on train, if the velocity of that ball is v ball, and the velocity of this train is v train, and the observer who is standing on the ground, he will observe the velocity of that ball will be velocity of train plus velocity of ball. You can consider a very simple example. You are moving on a train. If you are standing on a train, you are throwing a ball with 5 meters per second, and the train is moving with 60 meters per second. So if I am standing on ground, I will measure 65 meters per second to be the velocity of that ball. This is how we perceive the phenomena in classical physics. But this is not same for the relativity concept. In case of relativity, if I'm standing on a train and I'm throwing a flash of light, and this flash of light is consisting of photons. Now these photons are traveling with velocity c. This train is moving with velocity v train. So how much velocity I should measure from ground? I should measure the velocity from the ground as c plus v train. This is what my common intuition tells me, because in previous case I have got velocity of ball is equal to velocity of train plus velocity of ball, but same result I'm not getting in case of light. So this is what very special about light. So this was a very special property of light which Einstein has given. According to Einstein, no matter with what velocity you are traveling, the velocity of light will be always equal to c, not equal to c plus velocity of train. So this observer will observe the velocity of light to be c only, not velocity of train plus velocity of light. So this is the invariance of velocity of light. By using this postulate, we are having new transformation. Previously, we have studied the Galilean transformation. According to Galilean transformation equation, we have seen that the Newton's laws of motion are invariant under Galilean transformation. What were the Galilean transformation equation? Let me write it down. Those equation, this were the equation: x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, and t dash is equal to t. These were your Galilean transformation equation. But Michelson-Morley experiment proved this all equation to be wrong. That's why we need some new set of equation, and that set of equation are called as the Lorentz transformation equation. So this equation is no longer true for me, and I have modified this equation to this particular equation. That is, x prime is equal to x minus vt upon under root 1 minus v square upon c square. For y direction and z direction, as I have already told you that we are not concerning about y direction and z direction. So for the both direction, the coordinates will be same. And this is the very special thing. Now time, which was same in case of Galilean transformation, is no longer same in case of Lorentz transformation. It means that the person who is standing in a rest frame of reference will measure different time than a person who is standing in the moving frame of reference. And that is where the concept of time dilation comes from. This is time dilation. And one more thing, from this particular equation, the concept of length contraction we can understand. So length contraction. What is length contraction? Length contraction is just a simple phenomenon. If you are standing on a platform, a person is standing in train, and in that train, the person is having a rod whose length is capital L0. The length of that rod is in actual L0. But if that person start to move in that train with a velocity which is comparable to velocity of light, then that rod is not of length L0 for an observer who is standing on the platform. For the observer who is standing on the platform, that length will be shortened. इसका मतलब क्या हो गया कि अगर एक शख्स आपका ट्रेन के प्लेटफॉर्म ट्रेन पर खड़ा हुआ है, उसके पास एक रॉड है जिसकी लेंथ है 5 मीटर, और वो ट्रेन मूव कर रही है एक ऐसे वेलोसिटी के साथ जो लाइट की वेलोसिटी के साथ कंपेरेबल है, और ग्राउंड पे एक दूसरा शख्स खड़ा हुआ है और वो उस रॉड की लेंथ को मेजर करना चाहता है, तो अगर वो गैलीलियन ट्रांसफॉर्मेशन इक्वेशन का इस्तेमाल करता है तो उसके लिए उसकी लेंथ 5 मीटर ही रहने वाली है, क्योंकि यूनिवर्सलिटी है गैलीलियन ट्रांसफॉर्मेशन इक्वेशन के अंदर, लेंथ तो चेंज नहीं हो सकती। लेकिन आइंस्टाइन के स्पेशल थ्योरी ऑफ रिलेटिविटी के मुताबिक उस रॉड की लेंथ जो पहले 5 मीटर थी, जो शख्स ग्राउंड पर आपका खड़ा हुआ है प्लेटफॉर्म पे, उसके लिए उस रॉड की लेंथ 5 मीटर से कम हो जाएंगे। That length will be shortened for a person who is observing the same length of rod from the ground. This is called as the length contraction. So length is no longer a constant thing for me. Length of any object depends upon from which frame of reference I am observing that. This is a very nonsensical thing. This was very nonsensical thing about that time. But this is actual what happens. People, physicists at that time thought that this is something which is wrong. But these are all explanation. The explanation of these all laws were the result of an experiment which is called as the Michelson-Morley experiment. So length is no longer a constant quantity for me. Similarly for time, if a person who is standing on a ground, if he look at a clock which is moving with velocity which is comparable to velocity of light, so what 1 second mean for me need not to be 1 second for other person. If a person, you can consider a spaceship, and on that spaceship a person is going, and I am having a clock and that person is also having a clock. So what if I measure an interval of any event to be 5 seconds, but if I want to measure the same event in that frame of reference, that will no longer be 5 seconds, it will be greater than 5 seconds. This concept is called as the time dilation. It means that time flows differently for different observer in the universe, and this appears to be somewhat surprising, but this is the reality. Different observers in different inertial frame of reference measure different times. This is called as the time dilation, and this is from where we get the concept of time travel. If you start to travel with velocity which is comparable to velocity of light, if you travel with velocity which is less than velocity of light but comparable to velocity of light, then time will be short, time will be dilated for you. That is 5 seconds in this frame will be, let's say, 7 seconds for you. If you start to travel with velocity of light, which is not possible, which comes from the postulate of Einstein theory that nothing can travel with the velocity of light. But for time being, let's consider you are traveling with velocity of light. Then for you, the time will stop. And if you travel with velocity which is greater than velocity of light, time will start to flow back. Time will start to flow in backward direction. And that's why we have seen so many fiction movies in which it is depicted that time travel is possible. So according to Einstein's theory, it is not possible. But if I consider a hypothetical condition, if I travel with velocity which is greater than velocity of light, the time will flow in backward direction for me. So this was about time dilation. Now, same thing is true for the relativistic mass. That now again consider the same example. A person is standing on platform, a person is standing in train, and that person is having a ball of 5 kg, and that person start to travel with velocity which is comparable to velocity of light. Now the mass of the ball was 5 kg for that person, but if I am looking at that ball from ground, that will no longer be 5 kg for me. It will be something like more than 5 kg. Let's say it's 5.5 kg or 6 kg for me. So mass is not also universal. Mass is changing depending upon how we are looking at that mass. If we are looking at that mass from an inertial frame which is moving with velocity which is comparable to velocity of light, the mass is no longer a constant. And this is something which was experimentally verified. You know the cyclotrons. Cyclotrons are the accelerator in which particles are being accelerated. So if an electron is accelerated with 40% of the speed of light, what is the 40% of the speed of light? It is about 42 million meter per second. If you are accelerating an electron with this much velocity, the mass of electron increased by 1%. Okay, we know the mass of electron, that is 9 into 10 to the power minus 11 kg, 9 into 10 to the power minus 31 kg. So that mass will be increased by 1% if they are being accelerated by 42 million meter per second. So this is having the special theory of relativity, having the experimental evidences in case of. Now same thing is true from the same theory of relativity. The E is equal to mc square. This is probably the most recognized symbol of the physics. Everyone's know this equation, that is E is equal to mc square. This equation also is the consequence of the special theory of relativity. According to this equation, matter and energy are not the different thing, but they are the manifestation of the same thing. It means that if you place enough energy in one place, you can create matter, or if you make matter disappear, then there will be generation of energy. This goes against the laws of thermodynamics, because we know the first law of thermodynamics, that energy neither be created and nor be destroyed. It can be either converted from one form to other form. But this special theory of relativity goes against that very basic law of thermodynamics. To create energy, you are able to destroy the mass. And the same thing happens in nuclear fission reaction. In nuclear fission reaction, a heavy nucleus is targeted with the neutrons, and with the bombardment of neutron, you are dividing that heavy nucleus into smaller part. And when this transformation is taking place, there is the disappearance of some mass. And where that mass is going? That mass is going to get converted ultimately into energy. And this was the phenomenon which was used to make the atom bomb. If you all know the incident of Hiroshima and Nagasaki, that all nuclear experiment was inspired from the Einstein's equation, that is E is equal to mc square. So this was all about Einstein's special theory of relativity. I will little bit talk about Einstein's general theory of relativity. This is different from special theory of relativity. Special theory of relativity was given in 1905, and this general theory of relativity was given in 1950. So what is Einstein's general theory of relativity? According to Einstein's general theory of relativity, what we perceive as the force of gravity arises from the curvature of space-time. So according to Einstein, whatever concept of gravitation was given by Newton, that was missing something, that there was something which was missing in those law of gravitation. So Einstein modified that concept, and he tells us, according to general theory of relativity, what we perceive as force of gravity is actually the curvature of space and time. And this was one of the best description of how gravity works. Let me explain this to you by using this animation. This is your Earth, and this is your space-time curvature. So according to Einstein, this space-time whatever space-time is there around a planet, it will be getting curved due to this gravitational pull of this Earth. In similar way, if the light passes through a heavy masses in this galaxies and in cosmos, the light will bend up to certain value. It will bend through certain angle. So this bending of light was also explained by the Einstein general theory of relativity. Existence of black holes was also explained by this general theory of relativity. So this was the general theory of relativity, and the Einstein general theory of relativity says that gravity curves the space and time. The curvature of space time is due to the presence of gravity. And it is very surprising to know that the GPS which we are using to navigate, that GPS system is having the involvement of this relativistic effect. Because according to Einstein's general theory of relativity, the clocks which are there on ground, you are having a clock in your mobile, which is made up of, which is working on the oscillation of crystal, and there is another clock on that satellite. That clock is atomic clock. That satellite is moving with certain velocity. Because of this relative motion, there will be the lack of time between you and that satellite, between your clock and that satellite's clock. And you can see here, the net result is that time on GPS satellite clock advances faster than a clock on the ground by about 38 microseconds per day. So thus it appears to be very small, but this is a very huge difference if you transfer this time into location. So it may happen that you want to go to a position A on this earth by using your GPS map, and you are ending up at some other place. You are going to other place. So GPS system will not work if the clocks on the satellite and the clocks in your mobile are not synchronized according to special theory of relativity. So that is the equation of special, that is general theory of relativity, and which is actually inserted in that system of satellite so that both times matches up. So this was about the relativistic effect of GPS, and this was all from my side for today's lecture. Thank you so much.
Thank you, Sheikh Muhammad Wasim Sahab. Now, as the last part of this program is vote of thanks. I call upon Professor Sayyid Sultan, Department of Chemistry, Maulana Azad College, and coordinator of this series to propose vote of thanks.
Thank you, Professor Arif Saab, for providing me an opportunity to propose vote of thanks. First of all, I would like to extend my sincere thanks and gratitude to our beloved principal for providing online platform for every faculty member to expose their knowledge. Thanks, Vice Principal M.A. Bari Saab, IQA Coordinator, Dr. Aditi Bhattacharya Ma'am, today's speaker, Sheikh Muhammad Wasim, for his nice lecture on this topic, and Director in charge, Dr. Rafiq Zakaria Center for Higher Learning and Advanced Research, Professor Arif Patan Saab, who is HOD of Department of Chemistry, Azad College. Lastly, I would like to extend my sincere thanks to our dear colleague participant. Thank you so much.